Hello.
Hey, hello. How are you?
I'm doing well. How are you?
I'm good too.
Awesome.
So,
I'm Richard. So it looks like it's you going
yeah,
first, I believe.
yeah, it's my turn. So, given an array of integers, write a function that reverses the order of the first k element in the array. First k element in the array. Write a function pancake sort that sorts and returns the input array. You are allowed to only use only the function flip you wrote in the first step in order to make the changes. Okay. Analyze the time and space. Okay, so basically, there is a function which I have to write, which will take an input as an array, and then k is like the number of elements that I want to reverse. And
Exactly. Yeah.
if I give, for example, 2, so it will reverse the first 2 elements. And then I have to use this pancake sort function and utilize this particular flip function to sort the whole array.
Yep. Exactly.
And the solution is always possible, or can it be the case like by doing this it is not possible?
It should always be possible.
It should always possible.
Yep.
1, 2, okay, 4, 5. 2, 3. Okay, I'm looking at the example, so I'm just looking at like how many stages it will require to do this particular thing.
Uh-huh.
So so basically, so the array is 1, 5, 4, 3, 2, right? So
Yes.
if I so in this flip array, I can split this array into half and then send a section of this array into flip array, or is it like I have to pass always pass the complete array?
So you well you I wouldn't see a reason for you to pass like a section of the array. So you would have to. So it says the first k elements. So for example, if you choose three, where k is equal to three in this example, 1 5 4 3 2, you would flip 1 5 4 to become 4 5 1, and then 3 2 remains unchanged. And so you can't choose to flip like a middle section of the array. You have
Okay,
to choose all the way from the front.
always from the front and the complete array. Okay,
Yeah, exactly.
so it would be like, okay, the first I will say k is equal to 2, and it will
Hmm.
basically give me 5, 1, 4, 3, 2. Then basically I can say k is equal to, okay, okay, so my goal should be to make to bring the highest number towards the end, because I can only flip from the start. Um,
Okay.
so 5, 1, 4, 3, 2. Now if I give complete flip, right? So 0, 1, 2, 3, 4. So then it should be something like this: 2, 3, 4, 1, then 5.
What do you mean k is equal to five, right? For the five elements in the array?
Yeah, yeah.
Okay,
Um,
looks good. Yeah.
and then I can look. Okay. Okay, then I can find the next highest element, which is at 4, right? And
Okay.
so now k will be 3, and now if I flip it, it will be like something this: 3, 2, 1, then 5, and then maybe where I have already sorted, so it will be like 4. I flip it, so it will be like 1, 2, 3, 4, and 5. Okay, I think I got the algo. So basically, what I would try to do is I will try to find the highest element, right?
Right.
Whatever is present in my array, and I will try to bring it at the end of the array, right? By flipping it. So it will be like twice flip. So first I will bring it at the first zeroth index, and then I will flip it to bring it at the end of it. So
Okay.
by doing this, like I'm fixing that. So I am done with the like last thing, and then I can continue to find the next biggest element, and then flip it, and then put it into the right position.
Sounds good to me. So in this example, after you've done two kind of iterations, you move
Yeah.
5 to the back, you move 4 to the back. It's already sorted.
Yes.
But would your algorithm continue?
Um, Next big element. Yeah, I think no. So it will not, right? So basically, there will be a pointer that will be pointing to the most sorted position. So, for example, the at first it would be like I have to sort it, like put the correct element into the last element, right? So that pointer would be
Hmm.
something like this. So it will be pointing to 2. So if my current element is not, the maximum element index is not with the sorted index, right? If it is not equal to the sorted index, then I can do the flip. If it is equal, then I can simply, move to the left because it is already in place, right? So I don't have to sort then.
Okay. Okay. Sounds good to me. Yeah. So you do a little check, and then you check if it's fully sorted. Yeah. Sounds good. But um, one thing I would consider is, so you mentioned, for example, in this last iteration, um, you said, so right now we know that 4 and 5 are sorted, right, from the algorithm. We
Yes,
move them to the back, and you
yes.
mentioned to check the largest element, 3. We're checking that if the index is at the last sorted position, right?
Uh, no, so the position that I have to fix the new element. So now I
Right.
already
And
know like 4 and 5 is already in right place. So my current will be right here, and I have to fix this
right.
particular position. And my
And so how would you
max,
know that you don't need to sort anymore?
I don't need to. So yeah, so there will be 2 pointers, right? So the first pointer will be the max element pointer, right? And the second will
Right,
be
right.
like till uh, where sorted, right?
Sure.
So if I know these 2 pointers, so I know like till where sorted -1 should be the next element that I need to fix. And if my
Okay, so in
maximum
this
element
case,
is equal to the till next sorted element -1, if these index match, then basically
so
I don't have to sort it, right?
this is what it would look like, right? You know 3 is the last sorted index, which corresponds to 4, and 2 is your max element, which is 3, right? And so 3
Yes,
minus 1 is equal to 2, and so you're saying that because those two are equal, we're good to go, no more sorting needed.
yes.
Okay, so yeah, so I think that's really close, but what happens if um, it looks like this?
Yeah, yeah. So I will then move towards left, right? So I will check all the left elements. So it will be like order
Oh,
of
so you
n.
keep, okay,
Yeah,
gotcha. So you keep going. Okay, cool. Yeah, looks good to me. Do you want to go ahead and try to code it up?
sure. So like I said, like I will have 2 pointers. So basically, let's put the max element. Let's say right now -1, right? And max element index actually, and then you know and then I can have already sorted index is equal to, I would say, like len of array, right?
Yep.
So right now and nothing is sorted for me. So while max of element index is greater than equal to 0, I'm good to go. So this is my edge case. Now uh, max element is equal to max of array already sorted index. So I'm just checking out the max element that is like inside my given scope right now, right?
Yep.
So now I have to find the index of it for, so here I'm checking like whether the element is equal to the max element. If yes, then current max index. So current max index will be like index, and then I will break, right? Now I found the index of the current max. So what I have to do, I have to reverse this particular thing. Um,
Would it be better if you just called it flip array k so it matches the
oh yeah,
function that
right,
they gave
right.
you?
Yeah, 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 that's correct. So I have to write that function, right? So flip
Yeah.
array k. Forward. So start is equal to 0 and is equal to um, k minus 1, right? And then basically while start is less than and array of start comma array of end is equal to array of end comma array of start, then I can just increment it, right? So this will basically flip my array till that index.
Yeah,
uh,
looks good.
so now here I know the max element, so I can just simply call um, flip. I don't have to pass array here actually because it's in global scope, so I can just pass k just to be here, right? So I can just
Yeah.
pass the current max index plus 1, right? Um, and then it will basically flip my array towards that, and then I
Sounds
have to
good.
flip it again, right?
Yep.
Flip, um, flip it again from the already sorted index. So already basically this. Okay. Before this, I can do a check if um, array of, okay, not here. Um, if array of current max index is equal to array of already sorted, right? Then I have to continue. Not continue. I can, you know, reduce it else. Or what I can do is, just to be precise, I can have it like this because I have to do this every time.
Okay. Yeah, this looks pretty good. One thing I noticed right here is, so you set max element index -1 up here, but then in your while loop, you're checking if it's greater than or equal to 0.
Oh, yeah.
So I don't think it'll run.
Yes, that's correct. Let's put something like this because it will just set it right. So
Okay,
really
sure.
doesn't matter.
But then you also never change the max element index in here. I don't think you use cur max index, but max element index is never modified. So I think this loop will run forever. Could
Okay.
you maybe, instead of using
Yeah,
the maximum element index, could you maybe just use already sorted index? Would that be more helpful in trying to determine how many times you run it?
correct. So I can do this actually, and this will basically,
Okay.
I don't need this now, and the current max index will be taken care of.
Yeah.
And I've already, okay, yeah, I think, yeah, this looks good actually. So
Okay.
I'm finding the
Um,
max, then this, then I'm iterating, finding the correct index, then I'm checking if it is not equal to the else. Then I've been moving back and I'm moving till my array of index is greater than or equal to 0.
okay. So I'm just trying to think of the base case here,
Yeah,
where already sorted index is equal to 0. So when you've basically sorted the entire array and it's just running with 0. So you're trying to find the max here of an array colon 0, which is going to be
like 0,
an
right?
empty array. Right. It's just going to be empty.
No.
So,
So basically in Python, this is like excluded index. So whatever, so already sorted index is like the excluded index. So it will search
right,
an index before.
right,
So
right. So this will
if
be,
the
right,
uh,
array
okay, so you are
colon
saying
0.
like if the array is empty itself.
Yeah. So I'm just considering if there's anything
Okay,
that'll break
okay,
here.
yeah, yeah, correct. So that I can hear like if not array. So what should I return here? Basically empty array.
Yeah.
So that should take care of this.
Okay. Yeah. Looks pretty good to me. I can't see anything wrong with this. You go ahead and you can go ahead and try to run it if you like.
Sure. Undefined. Uh, max
Yes, I think that
argument
was what
is,
I was worried about. You're passing an empty array to max.
so this one is basically, actually I don't need to check for zeros, right? Because it will be
There you
already
go.
in the place.
Yep. Exactly. There you
Yeah.
go. Perfect.
Okay.
Awesome job.
Yeah.
You're the first
Thank
person
you.
to get that without any hints.
Oh, you asked this question to other people?
Yeah, this is like my go-to. It's like Pramp makes me ask this question every single time,
Oh,
and no one has gotten the way you flip twice and you move the last element to the last sorted index. That's like a huge revelation that most people have, and
yeah,
I'm really
actually,
surprised you got that. That's
it
impressive.
helped, just to solve it by hand here. So I got the
Yeah,
info
yeah,
here from here. Yeah.
that was really nice.
Okay. Thank you. So let's wrap the rules. It's your turn.
Yep.
Oh, sorry. Yeah.
Okay, so given two words, source and a target, and a list of words, find the length of the shortest series of edits to transform short source to target. Each edit must change exactly one letter at a time, and each intermediate word and the final target word must exist in words. Okay, so in this example, we're changing bit to dog. Mhm. Okay, so the I becomes a U, the B becomes a P, or yeah, and then the U becomes an O. Okay, and then the T becomes okay, so it's every letter. Okay. Um, let me write something down here. So let me copy this example. So we have bit and dog, and the words we have are these, right? So one thing I'm thinking of, right, there we know there's 26 characters possible, and let me just check if are they all lowercase words?
Uh, it is not written actually. You can assume, yeah, like don't assume like they are lowercase, I think.
Okay. But since we're changing, okay, I think I can still kind of get around that a little bit since we're changing each letter, and they don't care about the casing that. So
Yeah.
uppercase A is same as lowercase a. I'm just
Uh,
gonna assume that there's 26 types of letters.
yes.
I think that's a safe assumption,
Correct.
right? So okay, so hmm, um, kind of okay. So I'm gonna go like brute force right off the bat here.
Sure.
So if we have our initial word bit, so just considering the first character, um, so I'm thinking something like recursion. You could, for each character, there's 26 different cases, right? Or 25 other different cases.
Okay.
So the first, or 26 total, sorry. The first case is um, you don't modify, right? You don't modify anything,
Yeah.
the current index, and move on to the next index.
Okay.
So that in this case would just be still bit, right? And then in the other 25 cases, so case 2 to 26, we test every other character
Okay.
and then move to the next index. So this would become AIT, CIT, DIT, EIT, FIT, and etc. So and then we pass, and then for each of these cases, as we're checking for each of these characters, we also have to make sure that um, the new character, the word, the word with the modification is in the set of words passed in as the array, right?
Okay.
So if it's not, we don't have to check that case, so we can just move on to other cases and just move on to the next index.
Okay.
Um, so, okay. And then we also want to check um, if the word is equal to the target. And so this is our return case. This is when we're good to go.
Base case. Yeah.
Right, exactly. Yeah, let me label that as base case. Okay, so this is kind of like the basic structure of what I'm thinking of. And then we have to kind of keep track of some more information here. Okay, so if we want to keep track of how many letters we need to change or go through, right? Um, so along with the information we kind of pass to our recursive branch, I feel like we can kind of keep a count of how many times we've changed a letter. For example, in our original case, why don't I go ahead and make this a tuple? So I'm going to say bit, and I've changed 0 characters so far because it's our original word. And so, for example, when I make recursive calls, in this case, going off of this example here, there's a few ways I can change bit, right? So I can change the bit to but, and so but because I changed a letter, I'm going to add 1 to my tuple, and this is going to represent how many words or how many characters I've changed. And then same thing here, big, same thing with 1. I believe those are the only 2 here that
Yeah,
I can
that's
change
it.
to.
That's it. Yeah.
Yeah, exactly. So then I would go through another recursive call,
Mhm.
and so but can be changed to put. And I would add 1 again to my tuple in order to represent how many characters I've changed. Big can be changed to nothing, I think.
Okay. Big.
And so one thing
Yeah.
I need to be careful of is technically we can change but back into bit and big back
Correct.
into bit,
Correct.
right? So I feel like we need to keep some data structure, maybe keep some set of original words, or
Okay.
of words that we've traversed, right? So this is kind of like breadth first search, I think. So we keep some set of words um,
Um, Depth for search or
that,
breadth for search? You're doing recursion, right?
yes, but now I'm thinking, so I'm thinking like overall arching idea.
Yeah.
Um, yeah, so keep some set of words that we've already seen. And so this can get rid of the duplicates that we might run into.
Yeah. So
Okay.
then you have to take care also, like when you return into the recursive call, you have to remove that from the scene, right? Or else it will not be used in some other path. The words that you have already seen.
Right. So that's where it gets complicated. So now is what I'm thinking that recursion might not be the best idea.
Hmm.
So now I'm thinking like a BFS might be more effective in this example.
Okay.
Um, so maybe let me go ahead and enumerate another idea down here.
Sure.
So maybe instead of recursion, I have a queue, right? And so this is typical BFS, right? We start off with our original word, start off with bit, and I still want to keep that same idea where I try every other character. And I want to, so still try all characters.
Yeah.
Um, for all indices. So now I don't want to just look at one index and at a time and recurse. I want to look at every single possible way that this word can be changed. So in
Hmm.
this case, that would be 26 times 26 times 3 times. And check if word is in word array.
Okay.
So after I try that, I would add that to the queue, add those words to the queue.
Hmm.
Again, I would still have that distance measure. I think that's really useful
Correct.
for the number of characters changed. I think that's pretty useful.
Hmm.
Add words to the queue, add to the number of characters changed. Okay, yeah, I think this is going to be much better than the recursive one. So as we keep adding those characters to queue, so we pop from the front. That's our first step. Pop from the front of the queue
Hmm.
queue, and then we try those characters. We add those to the queue, and then at the base case, we want to be check if word is equal to target.
Correct.
In that case, return the corresponding number of characters changed, which would just be equal to, for example, if our node is equal to n, it would just be n bracket 1, since that's the distance.
Yeah.
And then in order to consider for the other case where there is no possibility to get to the target, So one thing we want to do is when we add these words to the queue, we also want to, after we pop from the front of the queue, we want to add this add word to list of seen words. So, or tested words. So these are the words we don't want to traverse again, if possible.
Okay.
So we add that word, and then once queue is empty, which it will eventually be empty since we're adding to this list of seen words, and eventually we're going to run out of, we're going to exhaust all the words in a word array. So once queue is empty, our loop is going to break, and then we return -1.
Cool.
Okay, I
Yeah,
think.
think this should work. So what will be the time complexity of this particular approach?
Yeah, so the time complexity here. Um, okay, time complexity is a little, for this one, so we have to check all 26 characters.
So,
Um,
yeah, actually, that was my next question. Do we have to do that?
right. So, okay, I don't see a way to not like kind of initially check at least. So like, for example, if I look at bit, I would need to check A through Z, but then I would have to also check if that word is in the array of words that were passed in. So we only put it in the queue if it's a valid word that we can use. But I think we still have to check if it's if we still have to like put the character there initially to see if that character plus the remainder of the word is in the array of words that were given. Are you saying that there might be a way to like not do that at all?
Yeah. So maybe instead of getting all the permutations of the words, maybe you can
Hmm.
just try to check with the words present in the array itself, right? And the all the words that have the difference of one.
Oh, yes. Yes, yes. Okay, so yeah, that's really smart. So you get the you so you go through the array of words and you check if you haven't seen it before. That's number one.
Yeah.
And then you check if the distance is off by one. So okay, so uh, check if word is equal to target. So try all characters. We don't want to do that. We want to try all words in word
Correct.
array. Check if it's not seen before, and if the offset is one character.
Correct.
Yes. Okay. So doing that, um, so it was the time complexity for this then. So the possibility is that we have to check all the words in the word array um, before we get to. So the possibility is that we have to end up going through all the words in the word array and then not reaching a target at all. So that's like -1. You had to go through the entire BFS, the queue. So the time complexity of that. So there's n. Let's say there's n words in the word array.
Mhm.
Um, I believe it'd be so for each word you have to check all the other words. So that's O of n squared.
Yeah.
Um, and then I'm thinking the testing if the word is offset by one. So in order to check that, you would have to check the length of each word. So if we,
So are you sure, like every time you will be checking all the words? So you're
so for
removing
okay,
it, right? So like
it's
your
true,
sample
it's
space
true.
is reducing every time.
So for bit, right, we would go through the entire words array. We would check every single one of those words, but put big pot, see if it's off by one. And then if they are, we add them to our queue and remove them from the words array. But there's a, oh, okay. So it's just,
Yeah,
I'm trying to
actually,
think, is it?
in worst case, you can take it as an O of n square. So
Right, right.
yeah,
Like if you
so
only add one word at a time, you start to check like n minus one words the next time, n minus two.
yeah, so it will be like multiplication of all, right?
Right,
Addition of
right.
all, right? Yeah.
So
So
I'm still thinking that's O of n squared. But then like checking each individual word, like checking if bit is one letter off to but, you have to check 3 characters, the
yeah,
length of the word. So I'm wondering, should I factor that in also to the time complexity?
yeah,
Okay, so if the length of the word, if it's like K, for example, K is the length of the word, the overall runtime would be O of n squared times K. So O of n squared K,
yeah,
since for each word we had to check it, and then there's possibility of n squared times.
correct.
And then the space complexity would just be O of n.
O of n, yeah, O of 2n because you're, uh,
Yeah,
yeah, that's fine. Yeah,
we have,
it's yeah,
yeah,
it's
yeah,
O of n essentially. Yeah,
yeah.
sounds good.
Okay,
Yeah,
cool.
let's code it.
I was, okay, let me get rid of my notes from the recursive call because I don't think that's useful anymore.
Yeah,
And just keep this queue here. So let's see. So I'm gonna start with the queue. That's gonna be my first thing. And it's gonna start with my source word. Um, and before I get anywhere else, I'm gonna define a function, check off by 1. So this could be a helper function that takes a word 1 and a word 2 and returns a Boolean if word 1 is exactly 1 letter off from word 2.
sure.
So I think the easiest way to do this is I'm gonna say I is equal to 0 and j is also equal to 0. So j is gonna be pointing to word 2 and I is gonna be pointing to word 1. So while I is less than length of word 1, j is less than length of word 2. Um, so the first case to consider is if word 1 I is equal to word 1 word 2 j. We can just increment both. Else they're not equal to each other, so the characters are different. I can actually say, so found diff is going to be a Boolean, set to false. And I'm going to say found diff is equal to true. So I'm going to first check. So if found diff is already true, it means we've already found a difference before this point, and now we have another character that's different. So in this case, we found 2 characters that's off. We return false.
Okay.
And then we reset true if we haven't found it before.
Yeah.
I actually don't think I put this here. Let me go ahead and change this just a little bit, make it a little more concise. So word 1, I is not equal to word 2, j. If found diff, we return false.
Actually,
Otherwise,
you can like take only one index also. So j is also not required, basically.
you're right. You're right. Is it guaranteed that all the length of the words are the
Yeah, if
same?
it is not like you can never like change a
That's true.
character and yeah.
That's
Okay.
true. So get rid of j.
So
We can
you
actually
can
just do
put a
this.
condition also like if the length of word is, different,
Yeah, yeah.
then you can straight
You're
off.
right.
Yeah.
You're right. So I can say if len of word 1 cool. So different lengths automatically rejected. Set a pointer. We haven't found a difference yet. We iterate through the word. If the characters are different, we return found diff. Otherwise, set it to true. We iterate through. Then we say return true at the end, since we have not found a second
Yeah.
difference. Okay, cool. So that's our helper function. And so now we have our queue. Okay, so I'm going to say visited words is equal to a set of words. Let's see. And then so I believe now, oh, one other thing. I want to make this into a tuple. Forgot about that. So this has to be 0.
Difference.
And so I can say now while queue. So while the queue is not empty, I can say our word is equal to q dot pop from the left. So the next thing we do is we add it to visited words. We also check if word is equal to target. That's great. And that's what we want. So then we just turn word offsets or changes. I think that's what we're changes. So and then we just add word is equal to target, return changes. Okay. So our next step is to try the words in the word array. Right. I think it might be better if I converted the word array to a set, so I can kind of get rid of words in there as well. So I'm going to do that. So I'm going to say words is equal to set of words. Right. So I'm going to say for word in words. Okay, so I'm going to go through and we check. So if offset by 1, or what's it called? Check off by 1. Check off by 1 of our, call this W, of our original word, and the new word is true, and W is not in visited words, then we can say q dot append, and we append a tuple of the word plus changes plus 1. Yes. Right. And so right now I'm thinking if I want to move or remove the word W from words. And I actually don't think we can modify words as we're traversing it. But I think that's okay. I think actually what I'm doing is redundant. So I'm going to remove, I think it's okay if I don't have it as a set. The runtime will still be O of n squared. So if I just keep it as a list, because I have the visited words like set where I'm adding every word that I see. So, and because I'm checking if W is not in visited words, and only in that case am I adding it to the queue, I think it's redundant what I was doing there by trying to remove it from the array of words that they gave me. So in this case, I'm just going to loop through, check if it's off by 1, and then check if it's not in visited nodes. So I'm going to append. And then I think that should be it for the BFS. And then in the case that our queue is just empty, return -1.
Okay. Check offset by 1 and W is not in visited words.
Yeah, do you want me to go in and run through and try to trace through the example just to see if this?
I think that would be better.
Yeah, let's try to do that. So just copy this. So we start off with a queue of just bit and 0. So our word is going to be bit, our changes is going to be 0. And so our visited words is going to be a set, currently with bit. So word is not equal to target, so we don't return yet. And now we want to loop through words. Let me copy the word array. Oh yeah, so we have, so first we're checking but, and we know that it is off by 1. So what we do is we append it to the queue, and our queue is empty because we just popped from it. So we append but with 1, changes plus 1. And then we check put, that's not off by 1. Big is off by 1, so we append that, big 1. Pot, not off by 1. Hog, not off by 1. Dog, not off by 1. Lot, not off by 1. Yeah, so that's everything in the for loop. So now we go back to the while loop and we do a dot pop again. So now our word is going to be but. Our changes is going to be 1. And our visited word is going to be bit and but.
Okay.
And so now we again loop through. It's not the target node, so we don't return. We loop through in words. We check but's already visited, so we don't even consider it. Put is off by 1. So let me get rid of but first because we popped it off. So now we add put, and now it's 2 now because we made 2 changes.
Yeah, I
So put,
think it should work. Yeah, I think let's
okay,
run it. Yeah, yeah.
cool. Oh,
Oh, you have to
indentation.
delete the comments. There is some bug with this editor. If you put the comments, it's sometimes give indentation error. So just delete off the comments that you have put, and
Okay.
it should work fine then. There are more comments I think
No, I
above.
think it's line 10.
No,
Oh,
no,
is it these comments up here?
yeah, yeah. Just try it. Okay, now there is some syntax error.
Hmm. Oh, oops. It's colon.
Yeah.
I'm ready. Okay.
Okay, undefined.
Oh, had a typo there.
Yes. Which typo
Another
changes?
typo. Another typo. I forget my variable names halfway through.
Yeah.
Cool.
Oh,
Yes,
good
that
job.
passed. Awesome.
Yeah. Yeah, you
That
got
was a
it
tough
in.
one. Dang.
Yeah. Yeah, it was an interesting problem actually. So,
Yeah. Was
getting with the
what was the
BFS
optimal solution?
was like a thing. So if you had gone via DFS, like it would have been inefficient because
Yeah, that's what I was thinking.
then you have to iterate over all the paths. Here, like whenever you get the target word, then you can return. But in that, you have to find the minimum path and then return, right? So
Right.
yeah. So I think yeah,
So was this the what was the optimal runtime that Pramp gave you?
yeah. This is the answer, right? So you have to do BFS over these words, and then
Is the runtime O of n squared times k as the length of the words?
yeah. So it's O of n square k.
Cool.
Actually, it's O of n k square basically.
Oh, where k is length of the word, so it's k squared.
Yes.
Interesting. Okay, I'll have to look at that after the session. But that's cool.
Yeah, because you are iterating over the words right once,
Right.
and then you are iterating for k for each words for checking offsets,
Hmm.
and okay, yeah, maybe yeah, it's fine. Something these time complexities actually. Yeah.
Yeah. Okay. Yeah, I'll look at that on my own time. But
Yeah.
yeah, thanks so much. You were a great interviewer.
Yeah. So,
Appreciate it.
let's. So, if you have a time, so where are you from? Like right now?
I'm from San Diego. What about you?
Oh, so I'm from India.
Cool.
Yeah. So, are you preparing for some job change
I
or?
I,
Yeah.
I am indeed. I have an interview in about 2 hours.
Oh, oh, cool, cool. So, I will not waste your time. So, okay,
Oh
all the
no, no,
best.
not at all, not at all. Do you have any interviews
No,
coming
no,
up?
no. So I'm just, just practicing. So I had already changed my company like 4 months back. So
Oh, okay.
yeah. So you
So
have
what
already,
motivates you to practice?
actually, I was thinking like I will create some YouTube channel, maybe,
Oh, that's cool. That's cool.
and it will like keep me in practice also, basically, doing interviews and all. So
That's smart.
that's
That's smart.
fine. Yeah. So yeah. So do you work somewhere or yeah, right? Right now you're a graduate or
So I'm going to school right now. Yeah. So I'm a rising sophomore.
oh, nice. So
Yeah.
it's your first job. It will be your first job.
Yeah. Basically. Yep.
Yeah. Okay. Chalo. All the best. Huh?
Thank
All
you.
the best for your interview. Chalo. Okay. Bye then.
Bye. Have a good day.
Yeah. Have a good day.